Good afternoon, everybody. We're going to start today Fourier series, and it will take about 2 lectures. And it will start from today, but we'll start important topics very involved in math, calculus, integration series. So pay attention, and if you have any questions, just ask, interrupt me, I don't mind. And if you are missing some formula, or you got some form of integration or series, just tell me, and I will upload it to the Fourier system. I'm trying to do my best to get the all formula that you need. I don't want to exhaust the integration or find the sum of series. So it depends on a lot of math, what's coming now. So Fourier series, that's the first topic will be used to analyze signals in general for continuous time and discrete time. So let's just discover what's Fourier series. Before we discuss Fourier series, the formula and how we perform this operation, just let's find why people ask for something like that. Why they need it? Usually we have in circuit, in any system, in any circuit, very simple system that we have here, linear 2-port electric network. We have input, we have output. The output has pi impedance. The output has impedance. The load. And I'm talking about now not DC. I'm talking about AC. The input is AC. It's easy if the AC is sinusoidal. If the input is sine wave like that, or cosine, whatever, it's like pure sine. Because in circuit analysis, when we deal with AC, when you take circuit 2, you will find we have very interesting simple tool called phasor. They deal with analysis using phasor, but condition, it has to be sine wave. When I say sinusoid, that means sine, cosine, shifted, not shifted, just this type. So this type of input, current or voltage, shaped as sine wave, it's easy to solve it by using something phasor diagram. And we can find the input and the output. It's not a circuit lecture. I could explain how we do it. It's very simple, but I'm trying to say that it's easy. But the problem, what happens if we have system or circuit and the input is AC, but not sinusoidal? That will be a problem. That's the first one that we face. Or we have sawtooth. In electronic circuits, you got many wave forms like that. So tooth, square wave, thing like it's not sinusoidal. So in this solution, yes, we solve it in time domain, but it's really complicated. Go through the rest complication in the time domain. But they said, okay, they try to figure out how they can solve this one. They have tool that's used to solve circuits and system that the input pure sine, and on the other hand, they have some circuit, the input is not sinusoidal. So they try to figure out, okay, if we can decompose this input or this source or this waveform into a series of sinusoidal waves, that would solve the problem. So, for example, if this sawtooth, if we could decompose it into a series of sinusoidal with different frequency, different amplitude, we don't care, just we want to have sine waves, then will be easy to solve it. And they found out that they can do that for most periodic waveforms. It has to be periodic waveforms, and there are conditions in it. It has to be finite, like not like this one finite. It's just it grows, it increases, and then stops and increases. But if there's something that going everything to infinity, it will not be able to do that. It has to be limited. So they found that we can do that. That would be sine wave of frequency f. This is 2f, 3f, 4f, 5f, and you look at that. You observe something interesting, that when they do that, they found that the biggest one, or You can say the greatest one, the fundamental, who calls the fundamental component. The first one appear for them called fundamental component. The frequency called fundamental. And then if the frequency of this one double the fundamental, we call the second harmonic. If the frequency of this component 3 times the frequency of fundamental, with third harmonic, and so on. Of course, connect to music, something like that, because it has frequency. So, and if you add it, then you can get this. Okay, that's great. If we can do that, that would be great. So who did that? Fourier. They could do create tool that express any periodic function. I want to say any, it means finite, I said, so finite. Any periodic function into series of sinusoidal waveforms with different amplitude, different frequencies, doesn't matter. Then you might ask, well, and how you're going to analyze it? Because you have, they told us the input is only one input here. You have now series. It's okay, because we are saying it's a linear network. You can do superposition. You get the first input, the fundamental, this one, you get the fundamental, you put it inside and see the output. Then put the second, the third, and then the sum, add all the response, then you get it. So it solves a lot of problems, this thing. Not only one application. This is one that I dealt with. I'm working with something like that. But there are other things. In electricity, power supply. The power supply provided by the utility company, pure sine wave like this one. The one to the left. That's a pure sine wave. Because generator rotating and all conductors distributed over the generator in sinusoidal way, and the output 3-phase, of course. Then we get 3-phase sinusoidal waves, pure. And the power is delivered to the customers, or we can say in engineering term, distribution station that will deliver to the houses, to industry. Then we have loads, like we have appliances, we have things, that's okay. But we still have load we can call it non-linear, because we have electronic appliances. And electronic appliances, it means that it has electronic switches, which is turns on and off. So it's like chopping the waveform, so it causes distortion in it. In industry, we have huge inductors, huge capacitors, huge equipment, especially the inductive load, and they cause distortion. You have furnace when they start welding or something like that, that's a high current. So it happens disturbance like that. So the waveform of the voltage in the transmission line, or because of the distribution system, it has distortion like that. So if this, and the problem that the power is polluted, and if there is one company or industry, they have some kind of machinery that polluted I call it polluted the power, and the shape of the voltage, it will go to the neighbor that they have clean equipment, and will affect it. And I had one experience with that. There was a cement company, and they have huge motor, huge, called induction motor, huge. It's like 4 times the size of this room. I was working inside. What happened? They have next to their company, some company they have furnace and have things like that, and use heavy machinery with high temperature, and when they make welding, so it has high surge current, so it causes really this distortion. So it went to the cement company, and the harmonics, we call this harmonics. When we have not pure sine wave, this is pure, one to the left, one to the right here, it's not pure, because it includes harmonics. What does it mean that include harmonics? It means if we analyze this one, we are not going to get only this nice, pure, clean fundamental component. No, we are going to get these components, which called harmonics. And this harmonics and the distortion, it causes overheating. This motor, the huge motor, it was the state of winding burn, and it didn't work and it stopped. When it stopped for 1 day, they lose $5 million for one motor for the cement company. So What's supposed to do? This is supposed to have filter. And this filter will clean the waveform from the harmonics. So to design the harmonic, you got to know what are the components of this waveform. What are the harmonics, the amplitude? Yes, you can make huge filter and then will clean all the harmonics because you make it design that it can like destroy any harmonic with amplitude 100 voltage or 1000 volts, but that's expensive because when you design the filter with big components, inductors and capacitors and things like that, that costs money. So you got to know the amplitude and the frequency of each harmonic so you can design a harmonic to just get rid of this component by the right amount. So you can choose the elements of the filter in the right way that can get rid of the harmonic. You don't oversize the filter. There are many things in the application of if you know the component of each one. Sometimes you compose them. So Fourier work on that, and you could express any periodic function by using this formula. X of t, this is the signal that you have. Obviously, function of time, continuous time signal. It said we can express it I don't like to write a question for you now. Just let me tell you what he can do. He said that if you have any periodic function, let's say something like that. And that's x of t signal, square wave. Doesn't have to be symmetric, it's periodic, just the condition has to be periodic, finite. Okay, so we can do it like that. We can say it consists of DC component. Let's call it x naught DC component. When I say x naught DC, that's DC component. What does it mean, DC component? It means maybe it has like DC like that by whatever value, 1 volt, 2 volt, like that. And some harmonic, like let's say A1 cosine omega t plus A2 cosine 2 omega t plus A3 cosine 3 omega t. We can continue. Then you, in general, you can have also sine. B1 sine omega t, B2, it's a series of B sine 2 omega t plus B3 sine 3 omega t till infinity. So in general, we can do that theoretically. What do we have here? What Fourier tries to say? Say that any signal, any periodic signal, has finite energy, you can, in general, decompose into DC component and series of sinusoidal with different amplitude, different frequency. What does it mean? Like this component, its frequency called omega. That's the first frequency. And the amplitude is equal A1. So you can sketch like cosine like that. And the frequency is equal omega. And another component, A2, but let's, before I leave, this is the amplitude is equal A1. So the height is equal A1. The second component, A2 cosine 2 omega t. You can have another cosine, but the frequency will be double the frequency that I just sketched here. And the amplitude will be A2. And you can continue. You have many cosines and with different frequency, but the first one, the first component here with this omega, this component was the fundamental component. And if you look at the frequency of the second, see 2 omega t, that's the second harmonic. 3 omega t, third harmonic, and so on. And then you can find the sine and the cosine. Say terms of sine, terms of cosine. And I will tell you why he makes sine and cosine. Said not only cosine. You can make it cosine, but to be shifted, like cosine omega t plus theta. So it doesn't make the shift, say the cosine sine. I will do that. We'll do both. But in general, it's a series of cosine and series of sine plus DC. The interesting thing about DC,
You can tell if this one has DC or not. Like I give you example. You have square wave. Let's just do that. It's a periodic. All right. And let's say that's plus 10 and that's minus 8. And the period here, let's say 0, 0.1, 0.2. So the period is equal 0.2 seconds. The question is, when you look at something like that, then I ask you, does this signal have DC component? So how can you tell it has DC component or not? Let me give you another signal and you tell me which one has DC component, which one doesn't have. Another one, similar to this one. $10 minus 10, 10 minus 10, the same 0.1, 0.2. T is equal to 0.2. Yes.
The DC component kind of meet in the middle of the trough.
What does it mean, DC component?
Like,
when you look at the one at the bottom here, what is the DC component?
0.
0. Because DC component means average. So the average of this signal, 0, because the positive area is equal to negative area. So this signal has a 0 average value, means that it doesn't have DC component. But the one in the top, if you look at the area, the positive area and the negative area, because the area here, equal area here, it's the width is 0.1, the height is 10, so 10 times 0.1 is equal 1. And this one, the width also is 0.1, because from 0.2 to 0.3, so you have negative 10 times 0.1 is equal to negative 1. When you add them, you get 0. So no average value. The average value equals 0. It means no DC component. But this one, it looks like the same one that we have, but shifted up. What does mean shifted up? It means you added DC component to make it go up. And I can tell you what is that. How you get the DC component here? Get the average. So what's the average of this one? The height is 10 and the width is 0.1, it's 1. And what about this one? That's negative 8 times 0.1, the same width. That would be negative what? 0.8. So when you add them, what you get? 0.2. So I can tell you that the DC component in this one, 0.2 voltage. 0.2 voltage. That's the DC component in this one. So DC component, you can tell when you look at the signal and you see the positive part and the negative part, they're not symmetric, or in general that the area, the total area is not equal to 0. That's what you can tell. So you got DC component and you got sinusoidal and cosine. So that's Fourier. What's right? So now you have DC component by finding the area over the period. That makes sense. This one will have a formula, but let's just talk about it a little bit. A1 cosine omega t plus A2. So it's like the sum of cosine terms. You have different amplitude, different frequency. What about this one? B1 sine omega t, it's sine omega t, fundamental component, amplitude is equal to B1. And the other second one, B2 sine 2 omega t. This is the second harmonic, the frequency double the fundamental, and the height is equal, or the amplitude is equal B2. So you got series of sinusoidal wave in terms of cosine sine. How we calculated, that's what we're going to see how Fourier did the formula. So that's A naught xt is equal A naught. What's A naught? That's the average. That's the DC component. How we calculated? First, we said that the signal x of t is a periodic signal. It means has a period. The period is equal t. So you say 1 over t. The integration 0 over t, it's the average. That's how we get the average by integration. So that's the DC component. And AK, the coefficient of cosine term. BK, the coefficient of sine term. Well, and this is the formula how you get it for AK, and that's the formula for BK. Again, what's AK? AK is the amplitude of cosine. And when you look at this series, AK cosine K omega naught T, all right, and AK is the amplitude of the cosine. That's how you get it from this equation. And K changed from 1 to infinity because we have A1 cosine omega T, A2 cosine 2 omega T, A3 cosine 3 omega T, and so on. You could substitute by K from 1 to infinity in general. Plus BK, the amplitude of the sine term, sine K omega T, also from 1 to infinity. But the interesting thing, they found out that every time you're getting higher harmonics, the amplitude gets smaller. Like A1 is the highest one. Then you find A2 small, A3 smaller. So that's when we do in the lab, we're going to truncate the terms up to 10 terms, and we'll find that it will give us very similar shape to the original X of T. Because supposedly that if you can decompose one signal into a series of sine waves, so if you add them, you get the same signal, right? But since it's not practical that we're going to add to infinity of series, we're going to just take like 10 terms and we add it. We'll find it's in the lab, it's very close to the original signal, which is okay. Very small error. So let's just take an example and see how we calculate this coefficient and the steps that we will take it one by one. Okay, I will let's pick an example here. Okay, we'll take this example. We'll work together with this example one by one, and you pay attention. It's a simple one. We have more complicated, but just we'll start with simple. That's the signal f of t. First thing, what you're supposed to do, check its period. Its period, yeah. What's the period of this signal? 2, right? Okay. So, and in seconds. So you say the first thing you do is say, okay, the period is equal. T is equal to. That's the first thing. 2 seconds. Then after you find the t, find omega. How you find omega? We did that in the beginning of the course. 2 pi over t. That's right. 2 pi over t, or 2 pi f, but we have t now. So 2 pi over t. So we have 2 pi over 2, which is equal pi radian per second. Call this omega naught. Omega naught, this is the frequency in radian per second. That's the fundamental. Oh, how you get the fundamental component from the period? The period of the function that you get it, and once you get omega, call it omega naught and say this is the fundamental component. This is the frequency of the fundamental component. This is the biggest one supposed to be. So we'll say that omega naught, that's the frequency of the fundamental component. If you are asked to find the frequency of the fundamental component in hertz, you can do that. How you do that? You will say omega equal 2 pi f naught. Then f naught is equal omega naught over 2 pi. Then you will say pi over 2 pi is equal 1 over 2.5 hertz. That's also the frequency of the fundamental component in hertz. All right, so the first step we get t, then we get omega naught. What's the third step? The third step, you get your sheet that has the coefficient, the equation of the coefficient. You're like, my days I have to remember those. No, but it's not practical, close. I'll get the sheet, and the first component I'm going to get the average value, or the DC component, A naught, call it A naught. All right. I'm going to write it down, the formula, and then I'll apply. A naught. Oh, but there's something before you do that. You got to look at the at this function. If you want to express this function in a mathematical way? Yes, you can. Let's just do it. So at least you get familiar with it. The function that we have, or the signal f of t, can be defined. Of course, I'm defining. When you have periodic function, you got to define the function over one complete period. Choose whatever, one complete period. You can start from the positive side, negative side, or half positive, half negative, but should be over one period. I would choose the positive side. I would say when the time from 0 to 1, it's equal 1. And from 1 to 2 is equal 0. That's it. I define over one period. 2, from 0 to 1 period. All right. So we'll go ahead, we'll start to write, I will write the formula and then we'll apply. The formula for A naught, the DC component A naught is equal to, it's like in the formula 1 over T integration over the period for the function dt. All right. So when I look at that, I know that the period that already we got it is equal 2 seconds. So I'll say 1 over 2. And then I'm supposed to integrate from 0 to 2. All right. From 0 to 2 for the function. But in this case, from 0 to 1 and from 1 to 2 is equal 0. So I will just integrate from 0 to 1. Because from 1 to 2 is equal to 0. So I will say the integration from 0 to 1. What is the function from 0 to 1? 1. Intentionally, I did it very simple. But it will be like that. dt equal 1/2. The integration of 1 is t. And the limit from 0 to 1. So you will have 1/2. And t substitute 1 minus 0. So is equal 1/2. So the average value is equal 1/2. The DC component in the signal is equal 1/2. All right. So we're done with the first term. And unusually, it's the easiest one. Now I'm going to get AK. AK, the coefficient of the cosine term. I will write also the formula and substitute AK equal 2 over T integration over the period f of t cosine k omega naught t dt. So the difference between A naught and AK, obviously, I multiplied by 2 instead of 1 over t, 2 over t. This is number 1. The integration the same over one period. But instead of integrating only the function f of t, I integrate the function multiplied by cosine k omega naught t. Why I added k? Because it's going to be a series and k will change from 1 to infinity. That's why. K usually integral from 0 to infinity. 0, 1, 2, 3, 4. But I'm not going to, when you do integration, leave it at constant. You are integrating with respect to t. So k will be as constant. Omega naught is constant. Second step, let me substitute now. Well, I will say in our case, AK will be equal 2 over t. T is equal to the integration from 0 to 2. I will write f of t like that. Cosine k. What is the value of omega naught? Pi. So you write pi. I'm replacing omega naught, pi. T dt. That's the first step by that substitution. But by what? By the value of t, by the value of omega naught. Then what you do next? Now we start to look at the function. Where it's defined. Is defined over 0 to 2 or only from 0 to 1 in this case, from 0 to 1. So I'll say equal. What's 2 over 2? 1. So the integration. From 0 to 1. Why 0 to 1? Because from 1 to 2 is equal 0. What is the function equal to? Is equal 1, as you know. So cosine k pi t dt. So simply in the end, I want to integrate cosine. What's the integration of cosine? I'll give you the table even if you forgot. The integration of cosine is sine. So not the differentiation, the integration, because the differentiation will be negative. When you can differentiate and flip the sign. All right. So equal to cosine. Let me refresh your memory. When you say what is the integration, let's put on side here. On the side here, when you say the integration of cosine alpha t dt, what you get? alpha, right? All right. So we'll do the same thing. Now we have alpha, k pi, all is like alpha, true? So the integration will be equal to sine k pi t over alpha, which is k pi, and the limit from 0 to 1. In what you'll do, substitute. You are doing integration. So you have 1 over k pi, it's constant. There's no t terms in it. Then you start to substitute by t. Sine k pi 1. See, k pi. Minus sine k pi 0. K pi 0 be 0. Now we'll find the value. 1 over k pi. What's sine k pi? You got to know it. Put k equal 1. You will have pi. What's sine pi?
0.
Put k equal 2. What's sine 2 pi? Okay. So that's equal 0. And sine 0, 0. So this term, unlucky, 0. What does it mean? We don't have cosine terms. Because an is supposed to be multiplied by cosine in the end. We'll do that. But an is equal 0. All right. It happens sometimes. You don't have everything. Sometimes you have bn, sometimes you have bn, and some cases you have an and bn. So we're starting with simple examples. So an equals 0. All right. But just remember what we did. I'm going to do now bk, and very similar to ak. The only difference you're going to do what when you get bk, you replace it. You replace cosine by sine. That's all. So let's do it. bk will be equal to 2 over t, integration over the period t. The function multiplied by sine k omega naught t dt. Now I will start to put the values of t and omega. T is equal to 2 over 2. The integration from 0 to 2. The function f of t, sine k omega naught is equal pi t dt. Now I will start to look for the function. I find again it's only defined over 0 to 1. So it will be equal to 2 integration of from 0 to 2 to 1. I'm sorry, because from 1 to 2 is equal 0, and the function is equal 1 sine k pi t dt. What's the integration of sine? Negative cosine. So be negative cosine alpha t. What's alpha now? K pi. Cosine k pi t divided by k pi, and the limit from 0 to 1. Now I'm going. There's something when you have negative sign and you want to substitute. I don't like negative sign. When I was a little kid, I have two things. I don't like negative. I don't like fractions. I don't know why. Do you agree with me with that? I never like negative numbers or fraction. So I get rid of it. How I get rid of it? I'll write just cosine k pi t over k pi, and then I change the limit. Instead from 0 to 1, 1 to 0. That will make up for the changing the sign. So now I just do cosine 0 minus cosine k by 1 means k pi, and everything is divided by k pi. Now let's look at that. What's cosine 0? 1 minus cosine k pi, everything divided by k pi. We have a story about k pi, cosine k pi. Cosine k pi, if you put k, let's just try. If you have k, let's say k equal 1. So what is the value of 1 or cosine k pi? But cosine pi by cosine with 8, negative 1, right? When you have k equal 2, so you will have cosine 2 pi, which is equal 1. And when you have 3, you got negative 1. You have 4, you got positive 1. So when k is odd, this one is negative 1, right? So we can say that cosine k pi, it's either negative 1 or positive 1. Negative 1 if k is odd. What does it mean? If k equal 1, 3, 5, and so on. Positive 1 if k is even, like k equal to 2, 4, 6, and so on. So let's find out what we get. So if k is odd, I know that cosine k pi will be equal to -1 if I substitute in the expression for vk that we have here, just to get some values. So what do you have? You have b1, right? Because when you put k1, b1, 1 minus minus will be plus over k pi. So it's equal to 2 over k pi. If k is even, let's make this k, cosine k pi is equal +1. In this case, bk, when you put +1, 1 to be 0. So you have only values for bk when it's odd. Now you have a0, you have ak, you have bk. I want to substitute in this ugly expression we see in the beginning. Well, let me write it down. And so the function f of t now I can express as a dc a naught plus. There is a sum, and the sum from 1 to infinity. And I got two terms, one sine, one cosine. The first one, an, that's cosine. Cosine what? K omega naught t. The same term I use in integration. Plus bn, sine term, sine k omega naught t. I know that an in this case is equal 0. What I'm going to do now, I'm going to substitute by the values. So a naught, I got a naught equal to half, if you remember, plus. Then I'll write k from 1 to infinity. Only I have this term. bn, I got a weird expression here. Oh, I'm sorry, bk. That's why I'm right in. That should be k. So I found bk equal to 2 over k pi only for odd. So I write this note bk. No, I have the value for bk. It's equal to over k pi sine k omega naught t. I know omega. Omega is equal pi. You got to put the value for omega naught pi t. But I got to put here odd. You have to put odd here. So let's take some 5 terms. So it means you have 1/2 plus, put k equal 1 in this expression. When you put k equal 1, you have 2 over pi, because k equal 1, sine 1 pi t. That's when k equal 1. Don't use k equal 2, because we said this expression only for odd. We'll prove that. So I take k equal 3. So you have this value 2 over 3 pi sine 3 pi t. That's when k equal 3. When k equal 5, 2 over 5 pi sine 5 pi t. I think it looks very, you can put 7 also if you like, but let me stop here. So that's the way you are going to express the periodic function. You can go up to 10, whatever you like. It depends on the amplitude. And look at the amplitude, the maximum amplitude 2 over pi. If I do it in the calculator here, 2 over pi, 2 divided by pi. That's equal to 0.6. Let me write it here. 0.5, that's the DC, plus the height of the fundamental component, 0.6366 sine pi t, plus The second one, it's 1/3 of the fundamental. I just divide what I have here, divided by 3. I got 0.212 sine 3 pi t plus what? I will divide it by 5. The fundamental component divided by 5. I get 0.127 sine 5 pi t. And if you wish to get the 7, I will divide it by 7. Just to tell you, it becomes now 0.09 sine 7 pi t. Can you see that every time the frequency is increasing, the amplitude decreasing? That's why when we design the filter, we don't care about the high frequency component. Was be gone, be very small, not effective, and you care about down in the front. Okay. There is some, yes.
Can you remind me why we counted by 1, 3, and 5?
Because when we calculated Bn in this equation, if you remember, we got it 1 minus cosine k pi over k pi. So when you put k 1, what you get? Cosine pi. What's cosine pi? -1. And they have negative in the front here. So be 1 minus 1 be plus 2. But when you have k even like 2, so what's cosine 2 pi? Positive 1. So what's 1 minus 1? So it happened that the even gets 0. Yeah. Yeah, I supposed to substitute by k equal 1, 2, 3 in sequence, but if I do 2, I get 0. Yeah. You're welcome. So when you look at that, now I know the components that they did something easy for engineering you can read. You call it spectrum, line spectrum. There is something called spectra of the any function here we do with Fourier. And line spectra has 2 things. Has magnitude spectrum and phase spectrum, because any signal can be expressed in the end by terms of sine and cosine shifted. So there is one for the magnitude and there is one for the angle. In this case, I will just make the amplitude. So how you do the spectrum for the amplitude? You will have like a horizontal line like that, and that's where you will have the frequency. You can write the frequency omega or f. Both are fine. I will use omega. And now let's go and see this frequency start from 0, and then the fundamental omega naught is equal to pi, and then we have 2 pi, 3 pi, 4 pi. Okay, let me make it a little bit. So that's pi, 2 pi, 3 pi, 4 pi. Of course, you can go up to infinity. What I'm doing here, I'm doing the fundamental frequency, and I start from 0, and then fundamental frequency 2, 3, 4, 5, multiply. 7 pi, 8 pi, and so on. 9 pi, you can continue. Then you go for 0. What is the amplitude of 0? Half, 0.5. So you choose your scale. I will say that's 0.5. So you will make straight line at 0. And the value here is equal to 0.5. What about the fundamental component? You have it here, 0.6366. Will be a little bit more than the average, right? So just let's say that that's the magnitude 0.6366. What is the amplitude of the second harmonic? 2 pi. 0. That's right. We don't have even. Yeah. So we have 0. Put 0 here. What about the third? 0.212. That would be, let's say, it would be like that. It could be shorter. Oh, yeah, that's right. Yeah, that's 0. What I'm doing, that would be here. That's almost 0.2, say. That's 0.212. What about the fourth? 0. The fifth? 0.127. 0.127. What about the sixth harmonic? 0. The seventh? 0.09. See, it's just, it's all, can you see it? So when you look at that, that's line spectrum. And this line spectrum, just you look at it, and then you know what is the amplitude of each component. And there's a spectrum analyzer in lab. When you look at it, it gives you the same shape here, and then you just look at it. When you put the signal, then you can, without doing, of course, Fourier, you just go. They do it for inside the software, and just to give you that. So you know, okay, when I design the filter, I have to get rid of course, you want to get rid of this, right? This is a vertical, what you wanted there. You get rid of this, and this. This is small, so I'm not going to design it for this one component. It's just enough if I get rid of the third and the fifth, that's good. The rest, negligible, very small. So you look at it and see what's happening, and then you design the filter. So, and now we have many instruments, just shows you the magnitude like that. But how did it? By Fourier series that we just did. And it shows you the frequency in the bottom in hertz, in regular, it will not tell you pi to pi, it will give you number. Give you 3.14 radian per second, or give you hertz. You can choose. Everything is available now. So that's the value of Fourier series. It will help us to solve the circuit. If you have something not sinusoidal, we have periodic. It helps us to design the filters. There are many applications. It helps also in the music because you can adjust the tone by seeing the harmonic. You add them, you get the tone that you want. And there's a program in MATLAB that you can add the frequency and you listen to the audio file, what you're going to get, so you can adjust it. So that's the story of the Fourier series, the basic one. We'll take more example because that was a simple example, but sometimes it's very involved. And I want to tell you how you can convert, because you have sine and cosine. You have sine and cosine. There is a way that to make it only in one term. But let me first write the trigonometric Fourier series, the traditional one that we did. We say that any signal x of t equal to the DC component plus, I'm just rewriting again what we did, from k equal 1 to infinity, an ak cosine k omega naught t plus bk sine k omega naught t. That's Fourier series in general. Sometimes they put it in compact form. What does it mean compact form? Only one term, cosine or sine, shift it. So I will give you the formula. Most of you will use cosine. So we'll say it's equal a naught plus sigma k1 to infinity, and let's use a k cosine k omega naught t plus angle, call it phi k. So that's another way to do it without using sine and cosine. You can just use only cosine or sine. I choose to use only cosine. So you see that why he was doing sine and cosine term, because it's shifted. In general, it's a sine or cosine shifted. So to avoid the shift, you can split it into two terms, sine and cosine. But now you might ask, what is the value of A? The value of A. Well, the value of A, of course, it depends on AK and BK, the small one. The value of AK, what do you expect? The A capital, the uppercase A. What's the relation between the uppercase A, this one, and the small a and small b? No. There is one, huh? The sum? Not exactly the sum. Because there is one sine and one cosine. What's the relation between sine and cosine? What's the angle between sine and cosine? What's the angle shape between sine and cosine? Yeah. 90, right? So there's one perpendicular on the other one, right? So B equal AK square plus BK square. Because sine and cosine, they are 90 degrees apart. So how we find the angle phi? Phi k will be equal to 10 minus 1 minus bk over ek. So these are the two formula to make it in general. If you want, we call this compact form, compact Fourier series. So that's compact trigonometric Fourier series. The other one, the traditional one, the classical one that we did, has sine and cosine. That's the basic. But sometimes some people, they get confused about the sign of the angle when the compact form. Sometimes because you don't know the negative, make it like I think I talked about the angle before. Could be adding subtracting 180, flipping. It's just could confuse. So the best thing to make sure that you got the right angle, you can express this thing like AK on angle phi k equal to AK minus J BK. If it's in this way, so you know what's the angle. Express it in complex way, so you know how you get the angle, in which quarter it is. It will tell you. Because of course, AK and BK can take any sign, can be positive or negative. Okay, so doing this, you will know which quarter, and then you can calculate. Or you can use the, as I said before, 8 and 2. That's to avoid this. So that's how we do it in compact form, and from compact form, you can do the line spectrum. Line spectrum now more general. What's line spectrum? Or sometimes you call it frequency spectrum. Let me just write frequency spectrum. That's one name. Another name, line spectrum. It has two parts. One part, it's the plots of the amplitude against the frequency. So one part will be the frequency. Of course, when I say frequency, it could be F or omega, and the amplitude. What is the amplitude in this case? AK, that's the amplitude. Let me write it clear here. With AK. So you have omega naught, 2 omega naught, 3 omega naught, 3 omega, and then you find A naught, A1, A2, and so on. And the other one, so this is a concern with the amplitude, and the other one with the phase. You are going to make a plot between the frequency, F or omega, and the vertical axis would be phi k. Yes. In the example that we just did, I did only one plot, the amplitude against the frequency. But what about the phase plot? Because as I said, line spectra has two. It's not only one, two. It tells you the amplitude, it tells you the shift phi. So how can you find the shift phi k in the example that we did? Let me refresh your memory. That's the formula in front of you. It's the tangent of minus bk over ak. What happened here in this example? That's what we have. So what do you think phi? If you want to find phi, of course there is nothing called phi 0, because DC is not sinusoidal, it doesn't have shift. You start from 1, right? So what's phi 1? Just you have here, that's f of t. You have here, it's given. The fundamental, this is the fundamental. That's the shift. 0.6366, that's the amplitude. That's it. But I want a phase shift. Let me show you the definition of the phase shift. By the way, this phase shift is easy. Usually we have to make calculation, but this is easy. Look at the phase. I told you that to know the phase or thing like that, just express it in this way. If you are confused, AK minus GBK. If you want to find phi 1, look for A1 minus JB1. Let's go back. What is the coefficient of the sine term? A or B? B. So you can say, if we write A is equal 0. We'll prove that all A's are equal 0 in the beginning, right? So 0 minus JB. What's the value of B? 0.6366. So what is the angle of this? The real is 0, the imaginary minus J whatever. -90. Yes. So the angle is -90. And when you look for each term, all of them will be the same, right? Because all are positive here, number, and all only sign. So all of them have 0 minus number, minus J number, 0 minus J number, 0 minus J number. So it'll be always -9. So if you wish to sketch the phase, I will do it here. That's omega 0 by the same thing. I'm using the same scale up. So at 0, of course, we don't do. For 1, minus pi over 2. So we just make line like that. Minus pi over 2. At 2, what is the angle at 2 pi? Yeah, we don't have component. We have only the odd. Minus pi over 2. It will be like a straight line like that. Easy. All. Because I don't have AM 0. 0 minus J something. Minus 90. So you have to be careful with that. The formula is there, but sometimes there's a special case. What happens if you have only AN and BN is equal 0? Yeah, so the angle will be? No. Only 90 when you have J. J, positive J, that's positive 90. Minus J, negative 90. 0. Yes. Oh, you cannot say pi. Pi is negative 1. Yes. This is the phase. Yeah, I'm going to I will write. That's the phase spectrum. That's the phase spectrum in red. And the one in blue, we call it magnitude spectrum. Magnitude spectrum. And both, you can call them line spectra. Because the plural of spectrum, spectra. So that's what you call it, line spectra. Or sometimes it's frequency. So that's how. So it's important if you can convert it to compact, then you can get both. We have some special cases if the function or the signal even or odd. It make it easier even. So let me show you the table when we have odd or even. I have in this thing brackets you're supposed to do and the answer. So you got to practice a lot with this one. I didn't do any complicated one. I will show you one integration, but at first I want to just to make sure that you understand. Now, I put in this table everything simplified. The first one to the left, general. This is general. It's not even. It's not odd. General. So that you can apply. That's the same. How you find a naught, how you find AK, how you find DK, and that's any periodic function. If you have even function, what does it mean even function? How do you know if you have even function? How do you know that? No. Exactly. It's symmetric about the y-axis. Then you will know. Like this one. I'm giving you an example here. Look, this is even. Symmetric about y-axis. Okay, you can check mathematically by one at the top there. If xt equal x minus c. The one in the positive and the negative, they have the same magnitude. All right. What happens if it's even? If it's even, bk is 0. If it's even, you don't have sign terms. Don't calculate b. You have to remember all special case comes in the exam. Calculate bk for the cosine wave or something even. Then you spend your time. No, just here. If it's even. What about a0 and ek? No, they have values. If there's any simplification for a0 and ek? Yes. What is simplification? In normal thing, you will say a naught, it's the average. You make the integration from 0 to t and then divide it by t. When it's even, you don't have to make integration over the whole period. Just it's enough to make it over half period. From 0 to t over 2. You make the half period, you make the integration, and then you multiply it by 2. Why? Because it's even. You don't have to make it over all period. You only make the half and then multiply. Why? Because the negative part here, like the positive part. So why you make it the whole integration? Make half of it, multiply by 2. Don't take it over one period, only half period. So that's another, that's simplification. You don't make integration for all period, only half. What about AK? The same thing. You multiply it by 2 and you make integration over half period. That's integration, the normal one, 2 over t from 0 to t. When it's even, 4 over t multiplied by 2. And the integration from 0 to t over 2. Integration over half period. Okay. That's two simplification. BK equals 0 and the integration over only half period. Right? What about if it's odd? How you know it's odd? Symmetric about the origin, or you have two reflection like this one. That's odd. Yeah. If you make one reflection on y-axis and another reflection on x-axis, you get it. Okay, that's odd. Or if you make any time here, that's the value. If you make the same value but negative, you'll find the same value but on the other side. We did that in the first classes. Okay. What happened if it's odd? Oh, that's nice. In A is 0, A 0, AK 0. Opposite for it. Any A. All right. What about B? The same thing. The same thing. Multiplied by 2, integration from 0 to t over 2, only over half period. That makes life easy.